Hi, welcome back. So today we're gonna continue our topic on the single source shortest path algorithms. So previously we have introduced Bellman-Ford algorithm, which works on a general kind of graph which doesn't have any constraints um, on the weights or on the properties of the graph. So Bellman-Ford algorithm will return a Boolean value, indicate whether there is a solution, right? So if that input graph has a negative weight cycles in it, then the Bellman-Ford algorithm will return false. Okay, so in today's lecture, we basically will look at algorithms that have some constraints or have some additional requirements on the input graphs. For example, first we're going to talk about how to find the shortest path in a DAG, which is directed acyclic graph. Okay, we already encountered this type of graph when we talk about topological sort weeks ago, right? So we're going to look at if that input is this special kind of graph, then what different kind of algorithms can be used to find the shortest path, and whether the different method can have some improved running time. Okay, so as we know that the Bellman-Ford algorithm is not a very efficient algorithm because its running time is big O of v times e, which is almost, you can think of it as a quadratic running time procedure. Okay, so now let's look at this single source shortest path on DAG first. Okay, so a DAG is a directed acyclic graph. So there is no cycles guaranteed in this graph. Okay, so we can utilize this property. And how do we do that? We simply rely on the results from the topological sort on this graph. Okay, so that we can improve the running time for finding the single source shortest path from the original big O of v times e to the current big theta of v times e. So it's basically kind of a linear running time function algorithms. Okay, so we have such an advantage because the input is constrained to be a DAG. So that means the DAG is acyclic and there is no cycles. So we don't. So that's the place that's the features that save us the running time. Okay, so to run this algorithm, we'll first start by running a topological sort on the DAG. Okay, and just a reminder that if you are not if you don't quite remember how topological sort works, you should now go to the slides in the elementary graph algorithms. So basically, topological sort relies on the depth first search that determines the discovery and the finishing time on the directed graph. And basically, you can use you can use one pass of the topological sort to record the discovery time and the finishing time, and then use a reverse order based on that finishing time to get a topological sort of all the vertices. Okay, so by the way, topological sort is a algorithm that applied to the vertices, okay, not to the edges. Okay, so then if the DAG contains a path from vertex u to v, then the vertex view must precede v. U must appear before v in the topological sort. Okay, so that's what topological sort does. So in the result of a topological sort, all edges are pointing from left to right. Okay, so no edges will be from right to left. So if a path exists, then the source edge must be be to the left of the destination vertex. Okay, so what we will do next, based on the topological sort result, is to make one pass over all the vertices in the topologically sorted order. Okay, then as we process each vertex, we simply call the relax procedure. Okay, remember we have a relax helper procedure, which is a quite simple function, which has just 3 lines of code with a one if condition statement. Okay, so we relax each edge that leaves the vertex. Okay, so we make one pass over all the sorted vertices, and for each vertex we encounter, we will relax all the edges that leaves that vertex. Okay, so that's basically the principle of how to find the shortest path on the DAG. Okay, so if we implement the algorithms that I described in the previous slide, it can be written in this procedure called DAG-SHORTEST-PATHS. Okay, which takes which takes the graph as input, the weight, and the source vertex S. Okay, so in line 1, it's just a topological sort. Okay, we call it topological sorts on the graph, and line 2 is the initialize single sort procedure, which is necessary for any kind of shortest path problems, shortest path algorithms, because we need to initialize the D properties to infinity. So in this procedure, we'll initialize all the D attributes to infinity and the pi to none for all the vertices. Okay, and for the source, the D would be the D attribute would be 0. Okay. All right. So, and as we know that the topological sort will take big theta of V plus E time. Okay, that's something you can look at in the previous slides. Okay, and the initialization takes big O of V time. Okay, so the key operations lies in from line 3 to line 5. Okay, so we have a 2-layer for loop, and in each in the outer layer, in the outer for loop, we go through all the vertices in a topologically sorted order. Okay, so that's a for loop that iterates over all the vertices. And the inner for loop, okay, what it does is to iterate over all the adjacent vertices of that current vertex U in the outer loop. Okay, and then for each adjacent vertex, we will relax the edge from U to V. Okay, so that's basically this inner for loop makes sure that we relax all the edges that leave the current vertex U. Okay, and we relax each edge exactly once. Okay, so that's easy. That's quite straightforward to get to know that the total running time would be big theta of V times E. Okay, because we relax each edge exactly once. So and we have E, the number of edges is defined by E. So the total running time is dominated by this big theta of V times E. Okay, so now let's just use a simple example to see how it works using this directed acyclic graph, so-called DAG. Okay, so if you are interested to examine whether there's cycles in it, you will see that this is a acyclic graph. Okay, so let's see how the algorithms runs on this simple example here. So after line 1 is executed, after the topological sort is done, let's assume that our input, the graph will have such a input graph will have such a new view, okay? And all the vertices are placed in such an order that all the edges are pointing from left to right. Okay, so that is the desired results from the topological sort. And also, after line 2, the initialize single source procedure is run, then we have all the vertices other than the source will be initialized with infinity to its D attributes. Okay, and also we have the pi attributes initialized as well. Okay, so the source is left with a 0 as its D attributes. Okay, so now what we're gonna do is to enter line 3, enter the for loop to go through all the vertices in the order from left to right, according to the results of the topological sort. So that means we will go to the vertex R first, and then we will relax all the edges that leave R in this graph. Okay, so I listed the relax procedure here just for your reference. So it basically compares the D attributes of V with the D of U plus the edge between U and V. So if the D of V is greater, then we need to update the D and pi of V. Okay, so that's what relax done. Okay, so in the first iteration, we have R encountered, right? So we need to relax two edges, which is RS and RT. Okay, so because currently the D of S is 0, it is not greater than the infinity plus 5, right? So, and the D of T is also infinity, it is not greater than the infinity plus 3. Okay, so nothing will be done in these when we encounter the R vertex. So we will simply go to the next vertex, which is S. Okay, so in this iteration, we need to relax Sx and St. Okay, so because previously T and X, they all have infinity values, and the D of S is 0, so that's why the infinity is greater than the SD plus the weight from S to T, which is 2, and the D of X is also greater than the SD, S dot D, plus the weight from S to X. Okay, so both conditions, so the if condition is satisfied, and we need to relax these two edges, and therefore we need to update the D's and the pi's of T and X. Okay, so update the results of updating the pi attributes of the vertices is that we highlighted the two edges, indicates the predecessor relationship or parent relationship. Okay, so these highlighted edges will form the shortest path trees eventually. Okay, so the next one will be T, right? So similarly, we can update Ty, Tz, right? And because the Tx, if you look at the edge Tx, the x dot d is not greater than the T dot D plus the edge 7. So 6 is not greater than 2 plus 7. So we don't need to update the D and pi of X at this step. So we just update Y and Z, okay, with the edges highlighted now. Okay, so the next will be X. So we highlight, we update the, as a result, we update the D's of Y, because 6 minus 1 is greater than the previous value, which is 6, but we don't need to update the D of Z. Okay, right? And then we go to Y, and to see if there's the updates, right? And it updates the d of z, right? And eventually when we reach z, because there's nothing, no edges leave the z vertex, so we're done with the algorithm. Okay, so far the results is pretty good, and the resulting highlighted edges show the shortest path trees. Okay, so now within all the nodes, rather than this R, we have 0, 2, 6, 5, 3, these numbers. So see, these numbers are just the shortest path weights. Okay, so it records the total sum of weights along the shortest path from the source to the current node. And because R is not reachable from the source S, so the D attributes of R still remains infinity. Okay, so that's it for the shortest path algorithm for DAG. So as you can see, it is faster algorithm than the Bellman-Ford, but it also has additional constraints on the inputs graph. Okay, so next we're gonna talk about a third kind of algorithm, which is Dijkstra's algorithm, to solve the shortest path problem with even more efficiency, much more efficiency. So Dijkstra's algorithm also has some constraint on the inputs graph. Okay, so it requires that all the edge weights should be non-negative. So the weights, all the edges should have positive or zero weights. Okay, so it's quite a different condition than the previous algorithms. So we shouldn't have negative weights for using Dijkstra's algorithm. Okay, so this is a pretty strong constraint. Okay, so what this algorithm, Dijkstra's algorithm, does is to maintain a set of vertices. Let's call this set S. Okay, and it will repeatedly select one vertex U from the rest of the vertices. So we maintain S, and what's the rest vertices is V minus S. Okay, so we repeatedly select vertex from the remaining parts with the minimum shortest path estimate, which is the minimum D. Okay, so we select the vertex from the remaining part with the minimum D and add that vertex to S. And then we relax all the edges that leave the vertex U. Okay? So it's a kind of a quite straightforward strategy. We just select the vertex that is seemingly correct because it has the smallest or has the lowest shortest path estimates. Okay, it is likely to be the edge. It is likely to be the vertex that leads to a shortest path. Okay, so it's kind of a greedy algorithm, right? So imagine that we want to find a globally optimal shortest path, but we don't know if the current option will lead to the global optimal, but it is just the locally best option, and then we just choose that one. Okay, so it's quite a typical greedy algorithm paradigm. Okay, so the key technical part is how do we select a vertex that has the minimum D value or D attribute. Okay, and the answer is also quite straightforward. It is a data structure that we used a lot previously. So we will use a minimal priority queue to maintain the remaining parts of the vertices, and that minimum priority queue is keyed based on the D values. So the vertex in the queue will be popped out or will be extracted if it has the minimum D value. Okay? So if we look at the pseudocode of Dijkstra, it looks like this. Okay? It has one line of initialization, which is a necessary part, and line 2 just initialize the set of vertices to be empty. Okay? And then we construct, at line 3, we construct a minimal priority queue with all the vertices in the graph. Okay? So the loop invariant is that the Q is always the difference between V and S. Okay? And then we enters a while loop. And this while loop will not terminate unless the minimal priority queue is empty. Okay? And at the first line of the while loop, we extract a vertex from the queue. Okay? And this code at line 6 is just a insert operation, right? We let S to be the union between S and the set of U. Okay, so this is just a insert operation on a set. Okay, so at line 7 to line 8, we just relax all the edges that leaves U and leads to V, and V is among the adjacency vertices of U. Okay, so it's not a super complex algorithm, but it's really easy to understand as long as you know the minimum priority queue and its basic operations. Okay, so the while loop will iterate exactly V times because it will not terminate unless it's empty, and because after we extract the U from Q, we will never insert it back, right? So that means each vertex in the minimal priority queue is extracted exactly once. Okay, and because we have V that many vertices in the queue, so that while loop will iterate exactly V times. Okay, so it is a quite typical greedy strategy, right? We always choose the lightest or the closest vertex in Q to add to S. Okay, and we will later, after we using an example to show how it works, we'll see that Dijkstra's algorithm is indeed correct, as long as the input constraint that no edge is negative is satisfied. Okay, so in the next slide, we're going to use an example to show how Dijkstra's algorithm runs. So we have an input graph like this with 5 vertices in total. Okay, and S is where we start the source vertex. So after line 1, the initialization is done. We have the D attributes initialized to infinity, right? So we will make a minimal priority queue like this with all the vertices in the graph from S, T, X, including S, T, X, Y, and Z. Okay, and the second row is the D attributes, right? Because S has 0 and it's a 0 here, and all the other values are infinity. Okay, and we also have S initialized to an empty set. Okay, so that's the initialized status of the Q and S. So then the while loop begins. Okay, we will extract one vertex from the minimal priority queue because S has the smallest number initially, right? So S will be the first one to be extracted, and the set will be the union between an empty set and the current small s, so source vertex. So S will be the single elements set of S. Okay, and the next steps from line 7 to 8 will relax all the edges that leave the source S, which is ST and SY, right? So we'll call relax on the ST and SY. Okay, and because T and Y originally have infinity values and S has non-infinity D attributes, so the D and the pi's of T and Y will be updated. Okay, so the highlighted edges show that the predecessor vertex of T and Y will be set to S, and their D attributes are also updated to 10 and 5 respectively. Okay, so that's the first iteration of the while loop. Okay, and remember that after T and Y are updated, the Q is also altered, because now we have different keys for T and Y, and the next elements or next vertex to be extracted will be Y, because it has the smallest key values. Okay, so in the next iteration, Y will be extracted. Okay, and S will be the union between the S and Y, which is 2 elements now. Okay, and all the edges from that leaves Y will be relaxed. That is from Y to T, the edge from Y to X, and Y from Z. Okay, and as a result, the D attributes of T, X, and Z will be updated, right? And the new predecessor relationship will be set by changing the pi attributes. Okay, and now the remaining vertices in the Q are like this. We have T, X, and Z, and then their new D attributes. Okay, so Z will be the next one to be extracted. Okay, so after Z extracted, S will be SY and Z, and we'll relax the edge from Z to X and Z to S as well. But as a result, only the X will be updated, because now its current because the original D value is greater than the D of Z plus 6. Okay, so the new predecessor relationship will be set for X. Okay, so its predecessor will be Z now instead of Y now. Okay, so the remaining Q is T and X, right? And the T will be the next one to be extracted, right? T extracted, after T is extracted, we need to update, relax on TY and TX. Okay, and as a result, the D of X and the pi of X will also be updated. Okay, so now only one element left, right? So after X is extracted, we try to relax the edge from X to Z, right? And eventually Q will be empty. So now when the minimum priority Q becomes empty, the while loop will terminate, and the resulting highlighted edges indicates the shortest paths trees, and the numbers of these indicate the shortest paths weights for all the vertices. Okay, so that's basically how the Dijkstra's algorithm runs. Okay, so one of the key question that people may ask about Dijkstra's algorithm is why it is correct. Okay, so it basically says that as long as we choose using the Dijkstra's principle to select the shortest, to select the current vertex that has the currently minimal value, then it will guarantee to lead us. It will guarantee to lead to the shortest path weights eventually for all the vertices. Okay, so in order to prove this correctness theorem, we basically want to show that at the moment that we select the vertex U and to insert it to S, right? We want to show that at that moment, the D of that vertex is already the delta, which is the global shortest path weight, right? It is the theoretically lower bound. Okay, so once we have shown that this is the case, this is true, then this equality will hold at all times after, right? So here in these two slides, I will show a basic, a brief proof of this theorem. And if you are interested to see the complete proof, you can go to the textbook. Okay, so we basically want to show some contradiction. If we assume that the vertex U to be the first vertex for which the D doesn't equal the delta when it is added to S. And under that assumption, if we have shown some contradiction, then it means this assumption is not correct, which in turn proves the theorem, right? Which means the UD should be equal to the delta. Okay, so there must be, so here's we begin the brief proof here. So there must be some shortest path from the source S to any vertex U, right? So we just let Y be the first vertex along the path, right? Such that the Y is out of the S. Okay, S is our already selected vertices, and Y is the first element, is the first vertex along the path that is outside big S, capital S. Okay, so and we let the vertex X be Y's immediate predecessor along the path. Okay, so we kind of decompose the shortest path from S to U into 3 parts, which is the first part is the path from S to X, and we call it P1, and the second part is the path from Y to U, which is P2, and another direct edge that connects X and Y. Okay? So that's a decomposition so far. And what we want to show is that because we let U be the first vertex that satisfy the D doesn't equal the delta when it is added to S, okay, then we must have the D of X must be equal to the delta of S to X, right? That's based on our assumption. So when X is added, right, according to the algorithm, according to the Dijkstra's algorithm, after X is added to S, then the edge from X to Y will be relaxed, right? So by the convergence property, if you go to slide number 59, you will see that because X, the D of X is already its global optimal value, is already the shortest path weights, and if we relax XY, then the D of Y will also be the delta between S and Y. The D of Y will also become the global optimal value. That's the so-called convergence property of the relaxation operation. Okay, and then we can observe a contradiction, right? Because Y appears before U on the shortest path, and all the edges are non-negative, right? From y to u, there must be some non-negative edges, okay? So then we must have that the delta of sy must be smaller than the delta of s between s and u, right? So the path between s and u must be longer than the path between s and y. That's for sure, because we have constraints that all the edge weights are non-negative, right? So we have such an inequality. The d of y, which is the delta between s and y, should be smaller or equal to the delta of s and u, which is also smaller than or equal to the d of u. Okay? Because both y and u are in v minus s, are outside s, okay? When we choose u, okay? But we choose u instead of y, so the d shouldn't be greater than, the d of u shouldn't be greater than d of y, okay? The d of u must be smaller than or equal to the d of y, okay? So that means the d of y and d of u must equal based on these two inequalities, right? They must lead to the equality between this delta between s and y and the delta between s and u. Okay? And it contradicts, right? So here we have the contradicts. It contradicts our assumption that the d of u doesn't equal the delta of s between s and u, okay? Which is good, because that means our assumption is not correct, okay? So that means our conclusion is that at the moment u is added to s, we must have the d of u is already the delta between s and u, okay? And that's the the brief proof of this correctness theorem done. Okay. So it also becomes obvious that's why we need a non-negative edges, right? Because in the proof, we have shown that if there are negative weights in a path, so it is possible that there are some negative weights along the path P2 that makes the d of u to be smaller than the d of y, right? Makes the delta of between s and u to be smaller than the delta between s and y. So we cannot always have this inequality true, right? So our previous inequality does not necessarily hold, okay? Which means we cannot make sure that at a moment u is extracted and inserted to s, its d is already the globally optimal value, right? So that intuitively makes sense, right? So because there could be negative paths in that are farther away from us, which makes our current local greedy choice not necessarily the best, okay? So that means if we want the Dijkstra's algorithm to work on the graph, we must require these constraints that all the edges should be non-negative, okay? So that's about the correctness of the Dijkstra's algorithm. And so next we're gonna briefly look at the running time of Dijkstra's algorithm. Okay, the basic cost is about maintaining the minimal priority queue, right? So there's some implicit cost of the insert operation in line 3, right? We are constructing a minimum priority queue here. And in line 5, we extract one element from the queue. And at line 8, after we updated some values of update some key values of the elements within the minimum priority queue, we must implicitly call some function like decrease key, or if we implement the queue with a heap, then we must call something like the minimal heapify stuff. Okay, so there are some functions implicitly involved in line 8 as well. Okay, so because each vertex U is added to S once, so that means each of its adjacent edges are also examined exactly once. Okay, so the for loop iterates a total of E times. Okay, so the for loop between line 7 and 8 iterates for E times. Okay? So the decrease key implicitly involved at line 8 will be called E times. Okay? So the running time of Dijkstra's algorithm depends on how we implement the minimal priority queue. Okay? I think we have mentioned that before. If we implement the minimal priority queue with a minimal heap, then most of the operations in the heap are logarithm. They are in the running time of the logarithm of v, which is the size of the heap. Okay, so the building of the heap takes linear time, and the extract min takes the logarithm of v times, right? And there are v such operations, and the decrease key at line 8 will take big O of log of v times as well, and there are e such operations because the for loops takes e total times. Okay, so altogether we can think of the running time as the big O of v times e, v plus e times logarithm of v. Okay, so if there are a lot of edges, or we can, if we think of v and e, they are at the same scale, same level, then we can use big O of e times log of v running time. Okay, so as a comparison with the Bellman-Ford algorithm, right? It's obviously more efficient in terms of running time. The Bellman-Ford is big O of e times v, but now we have an e times logarithm of v. Okay, so it's kind of a we can draw some analogy with some optimal sorting algorithm, right? So it's e times the logarithm of the number of vertices in the graph. Okay. All right, so that's so much for the Dijkstra's algorithm. Okay, and also this one can be further improved if we use some more advanced techniques. Okay, and in the last slide, we can simply wrap it up with the previously introduced advanced algorithms on the graph. So Dijkstra's algorithm is kind of resembles both the breadth-first search and the Prim's algorithm for finding the minimal spanning trees. Okay, and the set that we use in the Dijkstra's algorithm is kind of correspond to the black vertical vertices in BFS. Okay, and both Dijkstra's algorithm and the Prim's algorithm uses a minimal priority queue to find the lightest edge, the lightest vertex, given a set, right? And adding that vertex into the sets, and then adjust the weights of the remaining vertices in the queue. Okay? And Kraskow's algorithm, the Prim's algorithm, and Dijkstra's algorithm, they can all belong to the greedy algorithms category. Okay, because they all make locally best choices with the hope to achieve the globally best results. And fortunately, they all work as long as the input constraints are satisfied. Okay, so that's so much for the lecture for advanced graph algorithms, and hope you enjoy the homework, and hope these slides are helpful in helping you with the assignments questions.